Hello everyone, welcome to your final video for Business Cal 2020. This video is going to be essentially a pretty quick look into what is known as the Fundamental Theorem of Calculus. It essentially um, is probably one of the biggest mathematical advancements in the last couple hundred years due to what it unlocks and what it allows um, average people to do, to calculate, to evaluate. This area problem that we've been discussing this week so far, to try and find the exact value under a curve, you used to have to be one of the top tier mathematicians, scientists, thinkers in the age before Newton. But thanks to these ideas and coming up with this connection between derivatives and integration, it allows pretty much anybody, as long as you know derivative rules, to find now the area. And so this lesson, the goals here is to make that connection between the definite integral and the derivative. And then from that, begin to evaluate definite and then what's known as indefinite integrals, which you'll see in some of the practice problems. And so to kind of start here, just to review, the area under the curve of a function f of x here from a to b is given by the definite integral. So again, this integral here represents the exact area, no matter if it's a rounded edge or not. A is called the lower limit, is the lower bound, essentially at the left boundary point, left boundary wall, excuse me. B is the upper limit, or the upper boundary wall, or the furthest to the right. And then this integral is equal to the area of that shaded region. And so to begin looking at the fundamental theorem of calculus, what we're going to end up doing with this region is I'm actually going to let B, that upper limit, variate. In other words, I'm going to fix A. So A is going to be a set boundary point. But this wall right here, I'm going to allow to move. And so you'll kind of see this in the picture that I've got drawn right here. And so what happens then is my area, that shaded region, it depends on wherever I place this, right? Whatever I want to choose X to be. And because I'm using X as my variable, then I have to change f of x. And so I use a dummy variable. So instead of using X, I just call it f of t. And so that just makes this the t-axis. You could technically use any variable you want there, which is why it's called a dummy variable. It's just representing the input. It doesn't really have a full impact into our overall line of thinking. So don't let that throw you too much for a loop. It's just saying now if I want to find the area underneath this function f of t from a to wherever I want to put x, then that integral can be represented this way here. And that means my area is no longer a finite number. I have to represent it as a function, right? This is an input versus output scenario. The output when x is 2 is very different from the output when x is like 5. So we have now defined in terms of a relation once I fix my a. And so what we're going to do to help kind of explore this idea and this area function written and expressed as a definite integral is to actually fix a function for f of t and also fix a lower bound for a, lowercase a. And the easiest one to use is this one. So what we're going to do is we're going to start the integral at 0. So my lower limit's going to be at the origin. My upper boundary is going to be x. So we're going to get to choose where we want this to be. The function that I want to find the area under is going to be 2t, so it's going to be something that we can actually calculate. Because notice that geometrically, what I'm going to have here is then a right triangle, and we can use the formula 1/2 base times height to determine the actual shaded region, starting at 0 and then going to x. Now what we'll do is we'll just let x increase in integer increments. So we'll start it at 0, because I can't go any less than that. And then we'll go to 1 when x is 2, x is 3, x is 4. And the goal is to say, okay, well, as I let x increase, is there a pattern? Is there a way to represent what the area itself is doing? And so that's kind of the overall idea to what we're going to be doing and performing. So let's go ahead and get started with this one. So if I let x be equal to 0, then what that means is I'm calculating a of 0. Remember, that stands for x. So I'm plugging 0 in for x. This means that the integral, I'm finding the area underneath 2t from 0 to 0. Well, we discussed in the very end of the last video that if you're integrating from 0 to 0, I'm not going anywhere, right? There's no shaded region. Therefore, to start off, this answer is just 0. It's kind of pointless to draw the graph, etc. So if I want to increase it instead and look at and say x is equal to 1, then what I'm doing is I want to find a of 1, which is the definite integral from 0 to 1 of 2t dt. And so I want to find the area created between 0 and 1, which is this triangle right here. So this represents a of 1. And so I know I can calculate this by doing 1/2 base times height. So it's 1/2, my base is 1, my height is 2. And so I get that this area is 1. So when x is 1, I get an output of 1 for the area. All right, well, what about if x is 2? All right, so I've got that graph drawn here. We'll do x is 3 underneath. All right, so I'm actually going to move these graphs a little bit because they're not on the grid. There we go. All right, so let's let x be equal to 2. So then I want to find a of 2. This is the definite integral from 0 to 2 under 2t dt. So just to show you geometrically what that is, I'm going to draw a line here at 2. There's my x, essentially the slider. And I want to find the area created by the curve and this boundary right here. So that would be 1/2 base times height. So 1/2, my base is 2. The height is 4. Notice that this is essentially whatever my x is, and this is plugging it into the function, so 2 times x, so in this case 2 times 2. And so doing this algebra, I'm going to get 4. So when x is 2, I get an output of 4. All right, well, what about when x is 3? So again, I'm going to kind of fix the graph. Okay, so this means I want to find a of 3. So what's the area if I move the slider to 3? So 0 to 3, 2t dt. Again, I'm moving the slider now to 3, so I'm going to draw a vertical line at 3. And so I want to find this area here. All right, this area is a right triangle, so I can find its area doing 1/2 base times height. So 1/2, my base is 3. Notice how that's the x. And then this is going to be multiplied by 6, which is 2 times x. This is then 18 divided by 2, or 9 for the area. So just to kind of recap, when I do a of 0, I get 0. When I do a of 1, I get 1. When I do a of 2, I get 4. When I do a of 3, I get 9. I don't know if you're picking up on any kind of pattern. If you've got a guess, let's see if it works out when we solve for 4. So if I want to find a of 4, I want to evaluate the integral from 0 to 4 of 2t dt. So this is the area from 0 to 4 for this function. So I want to find this shaded region right here. All right, well, this again is a triangle. So it's going to be 1/2 my base, which is my x value, times 2 times that x value, which is 8, because that's my height. And so here I would get 16. All right, so notice again, that means when a is 0, we got 0. When x is 1, a of 1 was 1. When x is 2, we got 4. When x is 3, we got 9. When x is 4, we got 16. So what do you think we would get if I did 5 for x? Well, if you're, again, following the pattern, if I was to think about the equation, then a of 5 calculated would probably be 1/2 times 5 times 2 times 5, which is 10. And if I calculated this, this would be 50 divided by 2, or 25. Notice how this is 5 squared. All right, if I did a of 10, this would be equal to 1/2. The base would be 10, because that's how far I'm sliding out with my x. But then the height would be determined by 2 times x, which would be 20. And this would be 100, which notice is 10 squared. So what about if I just wanted to do this in general? If I just wanted to find the general equation for any x? So I have some kind of representation. Then a of x is technically 1/2 times x times 2x. And if you multiply this out, I get x squared. So in other words, a of x, which remember was this definite integral from 0 to x, 2t dt, is equal to x squared. That's the equation, that's the answer we would get out of this. So if you wanted to go all the way to 15, we wouldn't have to draw it out and do the area formula anymore for a triangle. We could just say 15 squared and say 225. There's my final area for that section. Well, there's another piece here that I want you to notice, and I don't know if you're fully seeing it, but if a of x is equal to x squared, what is the derivative of this? How is this area technically changing? Well, the derivative of x squared is 2x. Well, why is that familiar? Well, that's the integrand, right? This is lowercase f of x. So notice that by deriving a, I get lowercase f. So therefore, what's the relationship between a and lowercase f? Capital A of x is called the antiderivative, because a prime is equal to lowercase f. Right? This is the main definition for antiderivative, which, if you recall, just means to work backwards. Right? If I'm given a function, what did I derive that gave me that function? Right? It's this whole entire idea of going backwards. Well, then what this establishes is that when I'm solving an integral, which is what a of x is, right? A of x represents the area. If I want to find an exact area, then all I need to be able to do is find the antiderivative of what I'm integrating, right? What I'm trying to find the area under. That is the connection, and that connection is huge in terms of going through and solving problems. Because now, even if it's a curve like sine, cosine, an exponential, a logarithm, any kind of function that we can integrate, if I'm trying to find the area under it, all I need to be able to do is work backwards from a derivative. This connection is very, very similar to the ideas and the relationship between addition and subtraction and multiplication and division. All right, it says again that if I am to derive, if I want to undo that, I need to integrate. Okay, well, you may be looking at this and you may say, okay, well, I see that there could be some connection with the antiderivative, right? The area, when I derived it, it gave me x squared. But this was very, very specific, right? We had a very specific function we were integrating, which was 2t, or 2x, if you want to think about it that way. But we also fixed it at 0. So in other words, what happens if I don't do it at 0? Would we still get the same answer? Because again, we were looking at a very, very simple case. So then what I want to do is let's define a new function here. Let's say, let's let a be something different. So let's let a be equal to 2, just to pick a value. Then when I do my x as a slider, I have to have my x greater than or equal to 2. This was kind of the definition for the definite integral between my lower limit and upper limit. And then let's define the area under f of t is equal to 2t as this: b of x is equal to the integral from 2 to x, 2t dt. Now I'm not using a because I'm technically defining a completely different function, right? My lower limit is different, and the shape that would be sketched out, that region, would be different from a. I'm not going to get just a pure triangle anymore. So just to help show you what this looks like, I've actually got it written right here. Here's what the graph looks like. Notice that it's a trapezoid. So if I was to find this area, I would need to use the trapezoid formula. All right, so let's go through and let's look at a couple different values for x and see again if there's a pattern, if there's another way to represent another equation or something like that to help represent b of x. So we're going to do a very, very similar format where let's choose values for x, but I have to start it at 2, and then we'll increase it at integer increments. So that way we can kind of see in the answers if there's a pattern or not. So we'll start with x is equal to 2. So I've got the integral written out again because if I integrate from 2 to 2, I'm not covering any area. That area would be 0. All right, but what about when x is equal to 3? So when I've got something that's a little bit more interesting, all right, then I'm essentially finding b of 3 which is the integral from 2 to 3 of 2t dt. So what I'm going to do is come over here and I'm going to draw that boundary line for x here at 3. And so the region in question that I'm trying to find is this one. Now we could go through and use the formula for a trapezoid to actually find this area. But what I want you to notice instead, geometrically, is that that shaded region right there is the leftover piece of this entire triangle here, where I take away this one. So notice, if I was to find the overall area from 0 to 3, and then subtract from that the area from 0 to 2, that would give me the result from 2 to 3. So let me write that out. So in other words, what I'm trying to show you is that if I find the area from 0 to 3, and then I take away from that the area from 0 to 2, this gives me from 2 to 3. And hopefully it makes sense when you're looking at the bounds, because think about it like a number line, right? This one here is counting from 0 to 3. But then I want to take away 0 to 2. So I want to take all of this away. So then what's left? 2 to 3, which is what I'm looking for, right? And so these integrals in the areas work that way. So this expression that I've got written is fine. But this expression should be familiar, right? If I start it from 0 and I go to 3, that we've already done, right? That is a of 3. Well, 0 to 2 was a of 2 when I started at 0, right? Those are the upper bounds in the places that I've done. And I know then that a of 3 is equal to 9, because I'm just squaring that, minus a of 2 was 4, so I get the area as 5. And if you were to go through and do the trapezoid formula, you would get 5 for this. So right now, the observation is that if I'm trying to find b of 3, I can actually define it and determine it in terms of the area A that we already have found and used. All right, so let's do x is 4. So if I want to do x is 4, I'm trying to find the area for b, which would go from 2 to 4 for 2t dt. But like before, this is the same thing as finding the overall from 0 to 4, and then taking away the area from 0 to 2 again. Well, this is a of 4 minus a of 2, which is 16 minus 4, or 12. There's the actual answer to the overall problem. But again, I can actually define this in terms of a. Well, what about for x is equal to 5? So I would find b of 5, which would be equal to the integral from 2 to 5, 2t dt. Well, this is the overall integral from 0 to 5 minus the overall from 0 to 2. Well, this is a of 5 minus a of 2 again, which is 25 minus 4, or 21. There's the final answer. But again, notice this. Well, what's the pattern, right? When x is 3, it's a of 3 minus a of 2. When x was 4, it's a of 4 minus a of 2. When x is 5, it's a of 5 minus a of 2. So if I wanted to do this in general, b of x, well, it would be a of x minus a of 2, with the way that we've got this defined right now. Well, in short then, notice that b of x, if I wanted to figure out exactly what it is, it would be x squared, because remember that's what a of x was, and a of 2 is just a constant. I'm always subtracting 4 every single time. So I'm squaring whatever my input is and then subtracting 4. Well, if I derive b here, the derivative of x squared is 2x, but the derivative of minus 4 is 0, so it goes away. Notice that this is still the same thing as a prime of x, which is still the lowercase f of x. So no matter if we started it somewhere else, it's still just finding the antiderivative. And what's really interesting about this part is when you change that initial starting point, all it really adds in is a constant, because it's that constant, remember, that when you derive disappears. It goes to 0, and so it's not taken into account. So if you remember back with the antiderivative video, remember that when you're working backwards, when I find the antiderivative, you're always adding a plus c. Well, that plus c represents the starting point, right? It essentially represents the exact value, the initial value when my lower limit was 2. If I change that to 4, then that would be what plus c represents. And so essentially then a of x, if I wanted to, I could say a of x is equal to x squared plus c, and then it would be the general antiderivative for every situation that we have. And so if I wanted to write that, then what I would say is if I'm evaluating if I'm evaluating an integral and it's 2x dx, the answer is just x squared plus c, right? And this is called indefinite, right? If I don't have a bound set, if it's indefinite, then I just take account that it could start anywhere. So I just do the same thing, find the antiderivative, and then just add c to it. For now, we're just always going to have a definite integral. We're going to have these fixed bounds, and so then my answer will always be a very specific number. So in a long-winded part, what this is establishing again is the connection between integration and derivatives. What I kind of like to do with this and kind of say is if you're starting with a function, let's just say capital F of x, if I derive, so if I take the derivative, it's going to take me to a new function. But if I want to go backwards, I have to integrate that function. That's the relationship between the two. And it's more so established in the Fundamental Theorem of Calculus, part 1. So there are 2 parts to this overall fundamental theorem. We have just established the first one in words and using a very specific example. Here's the actual formal definition. So if f is a continuous function on a to b, then the area function a of x is equal to a to the x, or a to x of f of t dt is continuous as well. It's differentiable as well, meaning we can derive it. And so if I was to derive this, right, if I take the derivative of my area, if I'm taking the derivative therefore of this integral, the derivative and the integral cancel each other out. I am just left with the function evaluated at x. The answer is just f of x. Notice again that you are just left with what you were trying to integrate to start with. This is establishing that derivatives and integrals are inverses of one another. They share the same relationship and properties as if you were dealing with addition and subtraction or multiplication and division, right? If you have 2 things multiplying and you want to undo that multiplication, you must divide because division and multiplication are inverses. If you are integrating and I want to undo that integration, then I have to derive because they are inverses and vice versa. All right, and so part 1 establishes that. Now, if part 1 establishes the relationship, then that means if I want to evaluate a definite integral, then I just need to know how to work backwards from a derivative, because that means the function that I have is just the derivative. So I need to know the antiderivative. And so that's where part 2 comes in. So this is the part that you're actually going to use the most, especially in this class and your like final week, which says this: if f is continuous on the interval from a to b, then the definite integral is equal to capital F of b minus capital F of a, where capital F is the antiderivative of lowercase, right? If you were to derive whatever function you get here, it would give you the inside piece. That's that relationship. And notice then that the area here is just equal to the upper bound minus the lower bound being plugged in. And that's what we actually came up with here, right? If you notice, when I'm trying to evaluate this, it's just the antiderivative evaluated at b minus a. And it was true for everything up there. And so I've kind of got an example because this is going to kind of illustrate some new notation and kind of a step-by-step process here as you're evaluating. So let's say you were doing the integral from 2 to 5 for 2x dx. Well, what I would do first is I would find the antiderivative of 2x. So I would do the power rule. So add 1 to the power, divide by that power. And then I draw a bar here and I put 2 and 5 to represent where I want to evaluate and what I'm going to plug in. Now I can simplify this so the 2's would cancel. And then I'm going to evaluate. I'm going to plug 5 in. So I'll have 5 squared minus, and then plug 2 in. And so I get 25 minus 4, or 21, which this is the same answer that we got before, even the same step when we get to this part right here. All right, so to show you this again, let's take a look at example 1 and example 2. So in the previous video lesson, we approximated that the exact area under f of x is equal to x squared from 0 to 2 was 2.6 repeated, which is just the decimal for 8 over 3. Well, let's go through and show that that is the exact area for this. So let's evaluate this definite integral. So if I want to evaluate this definite integral, according to the Fundamental Theorem of Calculus, part 2, I just need to find the antiderivative of x squared. To find its antiderivative, we add 1 to the power, divide by that new power, and then I'm going to evaluate this from 0 to 2, which means I plug in the upper bound first, so this will be 2 to the third over 3, minus plug in the lower bound. And now I just need to simplify. So 2 to the third is 8 over 3. 0 to the third is still 0. Divided by 3 is still 0. We get 8 over 3, which matches. There's the exact area underneath x squared from 0 to 2. All right, well, what about if we look at a function that's a little bit harder? So example 2. Find the area of the region R under the graph of y is equal to x squared plus 1 from x is negative 1 to x is 2. All right, so this means that if I'm trying to find the region, then I'm trying to evaluate the definite integral from negative 1 to 2 of x squared plus 1 dx. Now, if I'm trying to do this, I need to find the antiderivative. Well, from the properties for the integrals and from doing antiderivatives before, this just means I'm going to find the antiderivative of each piece and just add the result together. So x squared, we've done that one before, just above. So I'm going to add 1 to the power, divide by the new power. And then the antiderivative of 1 is x. Now, I can double check this and make sure this is right by deriving this, and that should get me back to what's inside the integral. All right, now I'm just going to continue to finish this problem out. So I'm going to draw my bar. This is essentially reminding myself what I need to evaluate. So I'm going to plug in the upper bound. So this is 2 to the third over 3 plus 2. I'm going to draw parentheses to represent that. Minus parentheses. I'm going to plug in negative 1. So negative 1 to the third is negative 1 over 3. Plug negative 1 in for x. This is minus 1 again. Oops, sorry, my computer was going crazy. Let's just turn it back on. I just need to simplify this. Now, one of the tricks that I'm going to do here is this is 8 over 3 plus 2. I'm going to distribute the negatives. So this will be plus 1/3 plus 1. I'm going to add the individual fractions first because sometimes they can simplify. So like notice how that'll be 9 over 3, and then the 2 and the 1 make 3. So this will be 3 plus 3, or 6. There's my final answer. And that's the area of the region R given by the problem. All right, so let's look at example 3, and then we've got example 4, and then I think I have 2 word problems for you. All right, so evaluate the integral from 1 to 3, 3x squared plus e to the x dx. So I'm going to integrate from 1 to 3, 3x squared plus e to the x dx. All right, the antiderivative 3x squared. Add 1 to the power, divide by that power. So see how the 3's are going to cancel. So I'm just going to take them out. Recall from the antiderivative lesson that the antiderivative of e to the x is just e to the x because this derivative is e to the x. It's fantastic. Now I'm going to evaluate this from 1 to 3. So this means I'm going to plug in my upper bound first. So this will be 3 to the third plus e to the 3 minus plug in 1, so 1 to the third plus e to the 1. 3 to the third is 27. Now e to the 3 is going to be a decimal, right? Remember, e is just a number. It's 2.71828, blah, 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 blah. So when I cube that, I'm going to get a number, but it's a number that's a decimal that never ends, right? So I'm just going to leave it as e to the 3 because it represents that finite exact value. So I'm going to leave that. Then I'm going to subtract 1 minus e to the first power, again, just leaving that. So I can simplify the 27 minus 1, so I get 26 plus e to the 3 minus e to the first power. And there's my final. This represents the exact. Now we could approximate this if we needed to, but this is perfect. I don't need to do anything else with that. All right, so the next part, evaluate from 1 to 2. The function is 1 over x minus 1 over x squared. To make my life a little bit easier, remember for the anti-power rule, I need to get it written as something raised to a power, so no fractions, something like that. Now, generally, remember that when I do the anti-power rule, I would add 1 to the power and divide by that new power. So when I have x to the negative 1, it doesn't work, right? I get x to the 0 divided by 0, and I can't divide by 0. So hopefully you're kind of remembering that when you integrate 1 over x, its antiderivative is very unique, right? The antiderivative is specifically ln the absolute value of x. Minus, and then this one's fine to do, so add 1 to the power would give me x to the negative 1. And then when I divide by negative 1, I'm really just going to be changing the sign. So I'm just going to go ahead and do that now. And then I'm integrating this from 1 to 2. All right, so I'm going to plug in 2 first. So I get ln of just 2 plus x to the negative 1 is just going to flip the 2 to the bottom, so 1/2. And now I'm going to subtract off, plug in 1. So I get ln of 1 plus 1 over 1, which is just 1. Now, ln of 1 is equal to 0, so this entire term doesn't matter. It's pretty much gone. So that means when I distribute this negative here, I'm going to get minus 1. So 1/2 minus 1 is negative 1/2. So my final answer is ln minus 1/2. There's the exact value. And again, we can approximate that if we really want to, but we don't need to. All right, so let's look at two applied examples, and we'll be done. So you can kind of see where this will kind of fit in. It'll still kind of follow the same theme. Okay, so applied example 5, so population growth in Clark County. As the 20th century ended, Clark County in Nevada, dominated by Las Vegas, was one of the fastest growing metropolitan areas in the United States. From 1970 through 2000, the population was growing at the rate of 133,680 t squared minus blah, 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 from 0 to 3. All right. People per decade, where t is equal to 0 corresponds to the beginning of 1970. What was the net change in the population over the decade from 1980 to 1990? All right, so if I let p represent population, specifically, let's say p of t, population at time t, according to how t is defined in this problem, then if I want to find the net change, then what I'm looking for is p of, in this case, let's see, 0 is 1970. So 1 would refer to 1980, 2 would refer to 1990. So I want to do p of 2 minus p of 1. Right? I want to find the change between those 2 decades. Now, we talked about in the previous video that when we're doing a definite integral is an accumulation, right? It's measuring net change. All right, and even more so, if I'm trying to calculate this, if you think about what we're given, this r of t here, r of t is the rate the population is changing. In other words, if I was to derive p, that is r. In other words, p, what I'm trying to find here, p of 2 minus p of 1, that's the antiderivative. Look at it as the capital F in the definition for the Fundamental Theorem of Calculus Part 2. In other words, that net change there is equal to the integral from 1 to 2 of r of t dt. That's what it's actually calculating. If you were to find the area underneath that rate of change from 1 to 2, then what we're actually finding is the net change in people, right? The actual net change in the population, right? So when you integrate a rate of change, we are finding the accumulation of whatever that top quantity is. So we're essentially then going through, and if I'm finding that, I'm really just going through and integrating from 1 to 2, my r of t function, which is 133,680 t squared, minus 178,788t, plus 234,633. And I'm doing this dt. Okay, so now if this is what I'm integrating, the antiderivative of this, I'm just adding 1 to each power and dividing by that new power. So skipping kind of the algebra, I'm just going to show you the result. You should get 44,560 t to the third minus 89,394 t squared plus 234,633 t. And I'm evaluating this from 1 to 2. Using a calculator, plug in 2, plug in 1, and subtract what you get there. And you should find that the change in population is 278,371 between 1980 and 1990. Okay, so this is how we can use integrals to essentially calculate this net change. Okay, so for the final example, it's technically applied example 6. Production costs. So the management of Stettler office equipment has determined that the daily marginal cost function associated with producing battery-operated pencil sharpeners is given by C prime, and then you have the function listed there. C prime is measured in dollars per unit, and X denotes the number of units produced. Management has also determined that the daily fixed cost incurred in producing these pencil sharpeners is $100. Find Stettler's daily total cost for producing A, the first 500 units, and B, the 201st through the 400th units. All right, so first off, we're given C prime. Now, that means that C of X would represent the daily cost. The daily, I guess, total cost, right? Let me make sure to see if they said the word daily, so I'm not making that up. That's daily fixed cost. So let's just say total cost. That's what C of X represents. So then C prime would represent that marginal cost, right? How it changes per increment as we go up. If I'm going through and I want to find for the first 500 units, then essentially I'm looking for what's the change in cost from C500 minus C of 0. That's what I'm trying to find. Now, in the previous example, because of the relationship between C and C prime, this is the same thing as doing the integral from 0 to 500. For my function given there, 0.0, I had to count this like 4 times when I was writing this out. 5 zeros, I think still. Yep. X squared minus 0.006x plus 4 dx. This is going to calculate that net change there. All right, so then this would be equal to the integral doing the antiderivative, so that would be 0.00002 x to the third minus 0.003 x squared plus 4x evaluated from 0 to 500. Again, using a calculator, plugging and chugging, doing the arithmetic, you would get 1500. Now, this would be the answer to the difference between the cost at 500 minus the daily cost that we started with, C of 0. But that's not really what this problem is asking. This problem wants to know what's the total cost for just the first 500. It doesn't want to know what the difference is. So I'm trying to find what is C of 500. Now notice that C of 500, if I add this C of 0 over to the other side, I have then the expression for that. So if I know what C of 0 is, then I know what the cost at 500 is. And we are actually told that the daily fixed cost incurred in producing these pencil sharpeners is $100. That's my initial cost no matter what. Like if I don't produce anything, no matter what, it's going to cost me $100. So that means the cost of producing the first 500 would be $1,500 plus 100 or $1,600. That would be the cost in producing 500. Now, if I want to calculate the cost of producing the 201st through the 400th, then what I am doing is I'm going through and finding the difference in cost between 400 and 200. This means I'm trying to evaluate an integral from 200 to 400 for, again, my marginal cost function. So I'm going to copy that down because I'm going to be lazy here. Again, we already know what the antiderivative of this is. So I'm just going to copy that down again. But instead of doing it from 0 to 500, we're doing it from 200 to 400. So plugging and chugging here, you would find that the change in cost would be $552 for the daily total cost for producing the 201st through the 400th unit. And so this ends essentially business calculus. This is kind of the last topic that you discuss in a calc class. Again, there are some topics that we just didn't get to just for the sake of time and trying to help manage distance learning. So your final assessment will have problems based off of the definite integral. The ideas created by essentially the previous video and at the beginning of this video is really just setting up. So that way you could, setting up the definite integral to hopefully give you a better understanding of what it is and what it's doing. But actually, what problems will you have to do, or what we just covered in these examples, So you need to be able to do an antiderivative. So if you did not see that video, make sure you go back and look at that. That is foundational to this final fourth assessment that I'll post on PowerSchool Learning on Thursday. So let me know if y'all have any questions. You have 1 week left from the date of this recording. Proud of y'all. Stay strong, and let me know if y'all have any questions. Thanks for watching.